All right, hello there. This lecture will be entitled Acids and Bases 2, and the purpose of this talk together, we were in Acid and Bases 1, we were attempting to get through what we refer to as three acid-base theories, descriptions, definitions of acids and bases. And we were able to get through Arrhenius and Bronsted Lowry, but we were running at about that 22 minute time frame, which I don't like to try to not get past that. And we did not have a chance to talk about Lewis. So today we want to jump in and we want to look at these, and we want to maybe review a little bit here, but we want to spend most of our time in here. And we want to begin by understanding that these theories broaden our understanding of what an acid or a base is, or how it is defined, or how we would think about it from a chemistry perspective. And so we just jump in and we look and we say, okay, what did Arrhenius say? What did Bronsted Lowry say? What did Lewis say? And how does that broaden our understanding of this topic? So that's what we're doing. So we began really, and we won't spend as much time with Arrhenius because I really feel like that's fairly easy for you to understand. But by Arrhenius theory or definition of an acid or a base, you would have something that when in aqueous solution, and I just want to remind you here that, what does it mean to be an aqueous solution? Well, people hear the word aqueous solution, they automatically think aqua, part of that word aqueous. Well, let's just make sure we understand that in an aqueous solution, water acts as a good solvent. And so whatever it is that you have in water, if water is acting as a good solvent, due to its polarity, due to oxygen's electronegativity, then whatever that item is in water will come apart. We use words like ionize, we use words like dissociate, we use words like dissolve. We look at the solubility table and we use words like soluble and insoluble. And so what we have here is we have water, okay? We have, and we're making an aqueous solution, but what we really have is we have something that's being placed in water. Like for instance, HCl is a gas, hydrogen chloride is a gas, so maybe we're bubbling some of that into water. Or sodium hydroxide is actually a little small white pellet solid. So what we're doing is we're taking these items and we're creating an aqueous solution. Well, that tells you something, because you know that by chemistry definition, if we're creating an aqueous solution, then the item is indeed soluble. So in this particular case, when they ionize, okay, then they create ions. Hence the term, ionize. So we're getting this hydrogen proton because this electron is being left behind here. So we're getting this cation and we're getting this anion. Okay, but the real key to Arrhenius was, where is it coming from? And you can see, I've done this on purpose, you can see that the actual item that makes it an acid or a base, so this ion that is leading to the production of an acid, or this ion that is leading to a production of a base, is literally being brought, I always say brought to the party. It's being brought to the party by hydrogen chloride or sodium hydroxide. And then we discussed, what makes an acid and what makes a base. Well, so what makes an acid is a higher concentration of these hydrogen ions, which lead, as you know in our discussion, to the hydronium ion, okay, because of this attraction to water and these lone pairs. But this, if you have a good concentration of this, you're going to be an acid. If you have a good concentration of this, you're going to be a base. And then we discussed the fact that, and I know I'm moving fairly quickly, but you've already heard this, that these are items that are bringing the hydrogens, and these are items that were bringing the hydroxide. Okay, but that was Arrhenius, and but that didn't do us any good when we began to look at something like this, that in aqueous solution would create a basic solution, yet this is not bringing the OH with it, okay? So obviously we need to just continue to broaden our definition of acids and bases, because Arrhenius by itself would not be enough. So that let us dive into the second theory, which was Bronsted Lowry. Now, Bronsted Lowry, instead of focusing on, this idea of bringing an H or bringing an OH with you, it focuses on the hydrogen ion. So Bronsted Lowry is going to focus on the H plus. And remember, that's simply a hydrogen proton that doesn't have its electron. So by Bronsted Lowry definition, an acid was going to be a hydrogen ion donor, and a base was going to be a hydrogen ion acceptor, okay? So you remember that I showed you this equation. I remember that I told you that it's reversible. I do want to throw, once again, a quick reminder at you. And I don't even necessarily know about this equation. I'm just throwing this reminder out to you in general, that just because you have a reversible equation doesn't mean that one direction may not be, more prevalent than the other, okay? So this idea of equilibrium and this idea of reversible, remember that sometimes reactions proceed more in one direction than they do the other. So just remember that, file that away in your memory banks. All right, this particular reaction, we were putting ammonia gas in water, and we were getting the ammonium ion, and we were getting hydroxide in. So when you look at this as just a sort of a summary type equation, you can tell that because we're getting this, that we have a base. But what's going on in the reaction is what defines, Bronsted Lowry, or what the Bronsted Lowry theory states. And what it states is that you have water functioning in this particular example as a hydrogen proton donor, and you have ammonia, okay, acting as the hydrogen proton acceptor. Now, you're going to get a little farther along in this lecture, and you're going to realize that this has a lone pair of electrons. But right now, we're really not focusing on electrons because when we get to the Lewis at the end, and we're kind of talking about that third theory, we're going to focus on electrons. Okay, Arrhenius focused on what you brought, H plus or OH minus, right? Okay, Bronsted Lowry focuses on the H plus. And then Lewis is going to focus on electron pairs. All right, so here we are. We're in Bronsted Lowry. We have one item that's acting as a proton donor. We have another item that is acting as a proton acceptor. So by Bronsted Lowry definition, one of them becomes an acid and the other one becomes a base. Well, so here goes. An acid is a hydrogen ion donor in Bronsted Lowry, and a base is a hydrogen ion acceptor. So if this one is acting as your donor and this one is acting as your acceptor, then by Bronsted Lowry, water in this particular case becomes your acid and ammonia becomes your base. All right? But what I want to point out so that we don't lose sight of this, all right, what do you have in your, looking here and going this way, because that's the way we're going right now. What do you have in your products? Well, you have hydroxide. So overall, by increasing the amount of this, what is it? Well, you're right, it's a base, okay? Now, there was another idea that was put forth in Bronsted Lowry, and that was the idea of conjugate pairs. Conjugate meaning to go together, meaning to be in very close association with one another. Well, I just want you to kind of slow down, use a little common sense here. Obviously, don't you think these two are going to be paired? I mean, think about this, and don't you think that these two, are going to be paired? And think about the fact that this is a reversible reaction, right? So whatever the way it's behaving on this side isn't necessarily the same way it's behaving on this side. For instance, here you can see from the reaction, you can see that you've got a hydrogen being donated and accepted, but here it's going really the opposite direction, right? This is what you created from this action. So remember, this is your product from this reaction. But because it is reversible, right, then these would be your reactants, but over here would be your products if you were going this way. So what's happening is essentially just the opposite. And I think you can see that if you really just take a close look at it. You can see that this ammonia that was acting as a base, in this case, it's acting now as an acid because it's donating its proton. And here, while water was originally acting as an acid, now this OH is going to act as a base, okay? Why? Don't forget the fundamental definition, okay, by Bronsted Lowry. If you donate, you act as an acid. If you accept, you act as a base. If you donate, you act as an acid. If you accept, you act as a base. So, I say, kind of think about it as almost sort of a reciprocal relationship, right? And so, what you end up having is you end up having what we call conjugate pairs. So here and here is a base with its conjugate acid. Here is an acid with over here its conjugate base. Okay, now I recommend you slow down. I recommend you think about that. I recommend you pause, rewind, whatever you need to do. You know, you got to take it slow, and sometimes you got to eat your elephant one bite at a time, and sometimes you just got to chew on it for a while. But kind of try to get that straight in your mind while remembering the overall point about Bronsted Lowry acids and bases. Okay, so according to Bronsted Lowry, okay, if you donate, what? You act as a what? If you receive, what? Then you act as a what? If you donate, what? Then you act as a what? If you receive, what? Then you act as a base. All right? So Bronsted Lowry focusing on the hydrogen proton. Okay, now, Lewis acids and bases. I really like this Chemistry Libre site, so I'm going to take a quote from them, and here's what it says, and I'm giving them credit for this fully. It says, ideas in science never stay static. One discovery builds on another. Our concepts of acids and bases have grown from the fundamental ideas of Arrhenius to Bronsted Lowry to Lewis. Each step adds to our understanding of the world around us and makes the big picture even bigger. Okay? So just stick with me. So Gilbert Lewis proposed a third theory of acids and bases that is even more general than even the Arrhenius or Bronsted Lowry. A Lewis acid, now this is where you really need to key in because this is the third one and this is the last part. Okay? So Arrhenius, you had to bring the H plus and the OH minus with you. Bronsted Lowry, we're focusing on the movement of the H plus, whether you accept it or give it. Now, in the Lewis, we're going to concentrate on electrons. Okay? A Lewis acid is a substance that accepts a pair of electrons to form a covalent bond. A Lewis base is a substance that donates a pair of electrons to form a covalent bond. So a Lewis acid-base reaction is represented by the transfer of a pair of electrons from a base to an acid. Okay, now you might want to slow down, you might want to read that again, and you might want to look at this. All right, so here we go. So here's this equation that we had before, except we're going to look at it the way we did before, but we're also going to look at it slightly differently because here in a second we want to consider this. We want to consider this ammonia. Remember, we had ammonia a while ago. This was the exact same equation that we looked at when we were talking about Bronsted Lowry. So here we have the same ammonia, but I do want you to consider that in real life, it would have a lone pair of electrons, 2, 4, 6, 8. Remember, we want to reach the octet. All right, and it would have sort of this, this orientation. So here we have this NH3, and here we have water. Well, once again, we have this idea of this H plus, this hydrogen proton, coming from water and coming over here to make this same association. This is the same equation that we were looking at earlier. We're just looking at it in a slightly different way. Earlier, we just considered the H+, we didn't really consider the electrons. So now we're really even kind of considering why this happens in the first place, or how it happens, okay? From a Lewis perspective, NH3 is going to be the electron donor. Think about this. Why? Because it's the one that has the lone pair. Water is going to be the item that is going to donate, okay, this H+. So H+ is going to accept that pair of electrons. Remember, H+ is coming to the party. It's coming to the party with no electrons of its own, okay? So think about this. So now we have one that is acting as a donor, and we have one that is acting as an acceptor, and by definition, that gives us our Lewis acid and base. So this is going to donate, right? So what does that make this by Lewis definition? A Lewis acid is a substance that accepts a pair of electrons. A Lewis base donates a pair of electrons. So if this is going to donate, then it will become our what? It will become our Lewis base. If this H+ that comes from water is now going to accept, in other words, it's going to come in, I don't know if I show that, yeah. It's going to come in right here. It's going to form an association here, right? Remember, this is a proton, so now you got 1, 2, 3, 4. Remember, you can add up your protons and think about your number of electrons, okay? So that's going to give you this slight positive here, right? But this association, okay, is going to produce this in your products. And then remember, you're going to have a good portion of this, which is what makes you a base. Why? Because this hydrogen went from here to here, right? But for the purpose of Lewis acids and bases, keep seeing the big picture. Keep seeing the big picture. You have one that is willing to donate, and you have one that is willing to accept. So by Lewis definition, this becomes our base, and this becomes our acid. Because by Lewis definition, we are simply looking at this idea of electrons and whether the electrons are basically, in a way, whether they're accepted, or in a way, whether they are given. Okay? Interestingly enough, the Lewis is the broadest definition, extending to compounds that the others do not classify as acids or bases. So here's our last example. Our last example, now come on, think about if this was Arrhenius. If this was Arrhenius, I mean, we wouldn't even begin to be talking about this from Arrhenius perspective, because we're not getting any H's or OH minuses here, you know, and we're really not even talking, look at the equation. You can see that these two things essentially join together, right? I mean, if I was going to go back to what I learned about chemical reactions in this class, does that look like a combination? So, I mean, I don't see any OH minus, I don't see any H plus, and I don't see the transfer of any H plus. So if I don't see those things, I obviously don't see Arrhenius, and I don't see Bronsted Lowry. So the Lewis definition, though, of this still gives us an acid and still gives us a base. Well, how can that be, you say? Well, because this, as you remember, had this lone pair, and this was willing to come into and make an association with this and basically accept this pair. And that's a bigger discussion than I want to have right now as to why. It has to do with hybridized orbitals and such, but that's not the point. The point I want to make right now is that this is willing to give, essentially, and this is willing to accept. So by definition, by Lewis definition, this would be a Lewis base because it has, and it's giving, and this would be your Lewis acid because it is doing what? It is willing to accept. So Lewis really opens up our definition of acid and base to a much broader category, okay? Because we don't see we don't really see the items that we were seeing in Arrhenius or Bronsted Lowry. So this makes our definition even more encompassing. And that's something we'll continue to talk about together and we'll talk about in class. But remember one more time, by Lewis definition, if you are an electron donor, then you're a Lewis base. If you are an acceptor, then you are a Lewis acid. So here we had our Lewis acid because it accepted, and here we had our Lewis base because it was willing to donate or give. So this idea of what makes an acid or a base is really much broader than just sticking a piece of litmus paper in something and looking to see what color it turns. Okay? Have a good day.